continue to talk about each status flag from the E flags register. So in the E flag register, actually we have each bit to store the status flag. So they actually look like this. For example, I have 1 byte. So actually each bit is only 0 or 1. So we just say, for example, like that. So each status flag actually only occupy 1 bit is enough. So if the value is 1, that means that flag is set. Otherwise, that's clear. So here we show you a few important status flags we were using for this class. So the first one we call carry flag, stand for CF. So the carry flag actually we're using for the unsigned arithmetic calculation. So when you have unsigned arithmetic calculation, either you do the plus or minus. If you don't have enough bits to carry out, so the carry flag will be set. So did you remember actually last week you guys this week when we talk about the binary calculation. So then if you have 1 byte binary, add the other 1 byte. But in your 8th bit, maybe they need to carry out for 1 to the 9th bit. However, since we only have 1 byte, that 9th bit cannot be saved in somewhere. So then, right, at that situation, after the instruction, the carry flag will be set. So the carry flag using for the unsigned arithmetic, if they are out of range, they can be do the addition, carry out, or when you have subtraction, they need to borrow in. No matter which one, when you reach from 8 to the 9th bit, so then you have the range out of the range, so the carry flag will be set. So the other one we call overflow flag. Overflow flag very similar to the carry flag. The same thing is because the arithmetic out of range. But that specific overflow flag is for the sign arithmetic out of range. So remember we told you before, right? You have 1 byte memory. They are using the same bit value. Programmer decide this one byte I want to using for the sign or unsigned. So that's why if I consider this one is unsigned, I do the calculation. Then if the arithmetic out of range, carry flag will be set. But this 1 byte, if I consider is sign arithmetic. So if they're out of range, so then the overflow flag will be set. So that's the 2 status flag. So then we have the sign flag. The sign flag just means after your operation, they can be addition, they can be subtraction, can be any other instruction. But afterward, if your result, for example, if the result is here, if we consider this 1 byte is sign value, then the most significant bit, if they are 1, so then that means the result is negative, right? So the sign bit will be set. On the other hand, if sign bit is 0, that means your result is positive. So then the next one is the 0 flag. So the 0 flag, the same thing. Remember, all the status flag, they will be updated after each instruction. So after your instruction, if your result is 0, right, so the 0 flag will be set to 1. So then we have the auxiliary carry. So this one like the carry flag, but we call that auxiliary carry flag. That's because you carry from bit 3 to bit 4. So that means you see here, 1 byte is 8 bits, right? So then we only consider the last 4 bits. So if the last 4 bits, the bit 3 carry over to 4, so then auxiliary carry flag will be set. So then the last one is the parity flag. So the parity flag means the value, the sum of one bit, also be careful, it's the sum of the one bit, is even number. So the parity flag will be set. So for example, you can see here we have, in this 8-bit, we have 6, 1. So that's the sum of the one bit is 6. So that's even number. So the parity flag will be set. So that's the status flag. So remember, after each instruction, all the status flag will be updated. Just sometimes their value will change, sometimes they won't. So the next one we talk about MMX and XMM registers. So actually, we don't really use these two registers in our textbook. But one thing is good to know for this register. So you can see the MMX technology improved the performance of the Intel processor when you implement advanced multimedia and communication application. So that's why if you are interested about the multimedia, you want to have the register support for specific instruction. So then that you will care about the MMX instruction. So then XMM instruction registers, they are the x86 architecture. So they have the 128-bit register. So that's why you can see each register, they are really the long bit. So that's for the XMM. They're using to string the SIMD extension to the instruction set. So the same thing, they are all related to the multimedia and the video. So then it's not really we focus on in this class. So that's good to know for those information. So finally, at the end of this video, I want to talk about the floating point register. Yeah, because remember when we talk about the instruction execution cycle, our register control unit, they are in CPU, but also the floating point unit also in the CPU. So when we do the ALU, actually they are focused on the arithmetic logic unit. So that means is the integer calculation, addition, subtraction, multiplication, division. So then if you have a decimal number, we need to using the floating point unit to process the calculation. Here let's see the floating point register. The floating point unit, FPU, performs high-speed floating arithmetic. Because you know the floating point arithmetic, that you focus on the decimal digit. So they from Intel 486, the FPU has been integrated into the main processor chips. So that's why the floating point unit is in our CPU. So the floating point register, actually we total have 8. Each floating point register, they are 80-bit register. So you see here, that's the data register. We from ST0 to ST7. But each one is 80-bit. Also, you see that's quite a lot. So they're quite big. That's because remember when we do the decimal calculation, it's really more complicated. Because if you want to do the division or multiplication, your decimal point will be continue to grow. So then actually they are arranged in a stack. So that's why the stack we do one by one. They're using for all the floating point arithmetic. So you have the data register to store the data. Then you have 48-bit pointer register. So like your floating point, you need to have the instruction. You have multiple floating point instruction. So we need to using the floating point instruction pointer to point to the next instruction we need to work on. So then you have data point as well. Then you have the control register. They have the tech register, control register, and the status register. But in this class, actually, I won't focus on how we will do the calculation about the floating point. I just quickly to introduce you what register we have. So one thing is, you see from Intel 486, we already have 8 80-bit data register. It's already enough to do the decimal calculation. So what I want to focus is actually I just want to show you how can we do the floating point calculation. Because like we told you, in the memory, we only have 1 and 0. So 1 and 0, basically, they are integer. So then you will think about how can I do the how can we do the decimal calculation? So that's why here we will show you the floating point binary format. You can have 32-bit, 64-bit, and 80-bit. The same thing just like integer calculation. We just reserve specific location for the calculation. But one thing is, if you have 32-bit, right, they reserve 1 bit for the sign, a bit for the exponent, and the other 23-bit for the fraction part of the significant. So what does that mean? Okay, so that means here actually your normalization range is 2 to the negative 126 power 2 to the 127. So this one I want you to pay attention. 2 to the 127 power, we know that's very big, right? But what is the 2 to the negative 126 power? If you remember exponent, when you have the negative exponent, you just have your value to put in your you flip the value and you put in the diameter. So that's why here 2 to the negative 126. Actually, this one is not negative number. This one is just very small number because 2 to the negative 1's power mean 1 over 2. 2 to the negative 2 power mean 1 over 4. Then 1 over 8, 1 over 16. So that's our decimal came from. We don't really using the decimal. Instead, we're using the negative exponent for the 2. So then you can have your how accurate your decimal will be according to how big your negative exponent can be. So this one is we call the single precision. The range is from 2 to the negative 126 to 2 to the 127. So if you want to have even more decimal number, you see the double precision can bring down to the 2 to the negative 1022 exponent. So they have 64-bit. You even have the double extended precision. So that's why you see we talk about the decimal. You can see this number is so huge in the negative way. So that's why the decimal point actually is really long. So when you have a floating number, if you want to express in the binary number, how we will do is we always have the floating number represent in the exponent way. So you can see your exponent, of course, the n is we call the significant, like the bit where you store. So then your b to the east power, b actually will be 2 is the base because we always have 2 as the base. But e, the exponent, can be positive or negative. So on the other hand, when you see the binary number look like this, like 11.1011. But in this binary number, kind of like they have decimal points, right? But how we interpret is different. You can see before your decimal, right? This one is 2 to the 0's power. This one is 2 to the 1's power. So that's why we can have this part. But the decimal part actually means this one after the decimal point, we start from 2 to the negative 1's power. So this digit value is 2 to the negative 1. So then 2 to the negative 2, negative 3, negative 4. So even your binary decimal look like this. How they interpret the value, they're using the base is 2. So then after the decimal point, your exponent will be the negative value. On the other hand, when you see the 0.1011 in the binary, we're just using the half plus 1/8 plus 1 over 16. So then you have 11 over 16. So of course, this one you can convert to the decimal number.